Share this. And my slideshow is not, oh, here we go. Now it's working. Okay, so the first thing we did is we considered the ionization of a weak acid, right? And let's say that we use HA as the symbol of the acid. And the ionization, as we had mentioned earlier, let me see something. I'm looking for my little icon here. Okay. And I'm gonna use my highlighter. Okay, don't forget that we use that double arrow to represent something that is essentially, excuse me, that is essentially reversible, right? All right. So let's see if I can get this to work. Okay, and there's an ionization constant, Ka, that describes the equilibrium. This is a regular equilibrium constant. Don't forget that we write it this way because, as you remember, the water is not included because the water is actually the solvent here. So the idea was that because this is an equilibrium constant, products over reactants, the larger the value, the more stuff there's on the top, more product, and therefore the stronger the acid, right? So we saw that. And then we said that there's a table kind of like this one where you can see the different kinds of acids. And of course, the way you read this is on the left, you have the name, then you have the formula, then the structural formula if you need it, then the reaction for the ionization here. And this is the column that we're interested in, the one that says the Ka. So once you see that column, you see they're organized in order of, decreasing values here, right? And so the higher in the table it is, the larger the value of Ka, and therefore the quote unquote stronger the acid is. So what I want to start with today is showing us how do you do a calculation of pH for a weak acid. And we're going to choose hydrochloric acid for this example, all right? So that's going to be our next one here. Okay, so let me come back here. This is going to be our first question. What is the pH of a 0.50 molar solution of HF at 25 degrees? All right, and I think that you should have this in your handout. So this would be HF, that's the acid. And we're doing a shortcut version here where instead of writing HF plus water, we're just simply using a shortcut version where you just show just the two ions that are produced. So that way we can write our equation for the Ka this way, and we're going to look it up, and we find that the equation for Ka is, the value is 6.8 times 10 to the negative 4. So let's write out the equation again. And what I'm going to do now is I'm going to switch over to paper and walk us through this calculation by hand. All right. So let me come back here. Let me take this guy here and pin this video. And what I have here is the same slide that you guys were looking at, but now I have it on a piece of paper, and we're going to use it to write down the solution of this problem. All right. So here we go. So please bear with me while I work with these things here. Okay, so the first thing we have is this is a weak acid, right? This is a weak acid. We know that for two reasons. One, well, because we saw it on the table before, but also because from the value of Ka here, we see that it's a small value, and that tells us it's a weak acid. That means that unlike a regular strong acid like hydrochloric or nitric, we cannot simply calculate the pH from the molarity of the acid. So yes, what do we have to do is we have to build an ice table. Yes. So let's start over here by starting with our initial conditions. We're going to do molarity in this case. So at the beginning of the process, we would say that our acid is at 0.50 molar. And of course, at that point, there is no ionization. We're going to have a change in the molarity, right? That's the C. Now, normally when we did this before, we used X, remember? The problem here is that, well, at least for me, okay, this might not be a problem for you. For me, it's a problem. We're going to be writing a lot of these things in scientific notation, where you use that X there. And in my writing, it's typically hard to tell if I'm using something times 10 to the something versus the variable X. So what I do is I use a different letter for these problems, okay? So please bear with me. I'm going to use the letter Y. I'm going to say that this guy, let's say Y moles per liter of HF are going to ionize, which means that Y moles per liter of hydrogen and Y moles per liter of fluoride are going to be produced, right? So that means that at the end of the process, this is the end, I'm going to have 0.50 minus Y molar HF left over. And I'm going to have Y molar H and Y molar fluoride. Okay? Now, looking at the equation for Ka, right, which we had over here, we see that this is going to be the product of the concentrations of these guys, which is basically Y times Y, so that's Y squared, divided by the concentration of the acid, which at this point at equilibrium would be 0.50 minus Y. Correct? All right. And then that tells me, according to the equation here, to the value of Ka, that this should be equal to 6.8 times 10 to the negative 4. Right? Now, here's what we do here. Again, this is where chemistry goes in before math. This value is very small. It's very much smaller than 1. In other words, what it's telling me is that, essentially, this number here on the top is very small compared to the one in the bottom. And that means that the change that has happened in the molarity, the ionization of my acid is so small that we could say that approximately 0.50 minus 1, it's pretty much unchanged. All right? This is what we call the approximation method. Now, we'll talk later on what are the limits to this kind of approach, right? This tells me that essentially the change that has happened in the level of HF, the unionized acid, is so small that it's imperceptible. It's like saying, whatever Y is, it's somewhere like in a decimal place out here. That's kind of beyond the level of precision of my measurement anyway. So that means that I now can change this equation into simply Ka equals approximately Y squared over 0.50, right? Because I said this is approximately unchanged. And again, we said this is 6.8 times 10 to the minus 4. Don't forget that we don't put units on equilibrium constants, at least in the way we do things here. All right? Okay, so what I want to do now is let's rearrange this and solve for Y. So Y essentially is going to be the square root of, I'm going to move this guy over here, 0.50 times 6.8 times 10 to the minus 4. correct? And if I have my calculator here, we can do this. Yeah. All right, so I have 0.5 times 6.8 to the minus 4. That equals that. And I'm going to take the square root of that, which in my calculator, you do it this way. And I get 0.01843988, blah, 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 blah. But remember that my input values here only had 2 sig figs. So let's say that this is going to be essentially 0.018. That is the value of my unknown. Now, remember, Y is essentially, as we saw back here, remember? Y is the molarity of the acid, right? And we're saying that that's 0.018. So if I want to calculate the pH, okay, that would be minus the log of H plus. In other words, minus the log of 0.018, which would have been, I'm going to take the log of this, and then I'm going to take the negative 1.73, blah, blah, blah. Don't forget what we talked about in our previous class. When you're working with pHs, the number of sig figs in your input number are reflected in the number of decimals after the whole number here. So in other words, the 1 does not count towards sig figs. I need 2 decimals for 2 sig figs. So I'm going to round this up to 1.73. And that would be the pH of this solution. Okay, I'm going to explain in a moment if this works or not, okay? Just as an aside, let's pretend that this had been HCl instead of HF, all right? So let me come up here and write, if this had been HCl, the pH would have been minus the log of essentially the molarity of the HCl, because we assume that it's going to completely ionize, we minus the log of 0.50, and that would be, so you can see, 0.30. So you can see that if this had been a strong acid, the pH would have been much, much lower than it is, because this is a weak acid and doesn't completely ionize in here. Okay? All right, let me take a little pause here, see if anybody has any questions. See, what I'm going to do is, if I'm able to do this later on, I will try to post pictures of this. Okay.
Can you put it up just a little bit more so we can see the bottom?
Oh, I'm sorry. Yeah, it's just that I got something in the way here. You know, tell you what, I'm gonna, let me zoom it in a little bit. There you go. Now you see the whole thing. Okay, any other questions? Some of the technical aspects here, I might not be able to see that somebody's asking about thing. There's a few questions here that had to do with technical stuff. I honestly don't know what to say. I'm just showing here the page where this thing is. I think you guys can go in your screen. You can find this page that I'm using. And basically there should be like a 3-dot thing on the top, and you can pin it so that it'll show up as your big screen on your computer. I'm hoping that's what it is. All right. Any other questions so far? Okay. All right. So let me come back here. And I'm going to come back here to my face. And then what I'm going to do next is I am going to see oh, here we go. Hold on a second. I lost my pages here. I totally lost my pages here. Hold on. Let me move this out of the way. I did that. I did that. I can't find my pages. I'm assuming this is it. All right. Let me come back to the next slide here. Again, I'm going to pin this page again. So this is our next question. When can I use this approximation? Now, in the previous exercise, let me zoom a little bit in here. And again, like I said, what you can do is in your screens, you should be able to pin this page as your main screen. And that way you can see it in large size. All right. Okay, when can I use the approximation? This is what we said last time. We said that because the value of Ka was so small, you could assume that the change in the molarity of the acid was negligible. And so you could use the initial molarity of the acid as if it's staying that way throughout the process. So the guideline here is when this value y is less than 5% of the value from which it is subtracted, that is when you can use it. So in our example that we just did, right? In the example we just did, if I can find it again, I'm losing my pages here for some reason. Oh, sorry, it's underneath here. Okay, so here was the what we said. We found out that our value of y was 0.018, right? So we said that y was 0.018. Let's see how that compares with the initial value, 0.018, all right? We're going to divide that by the initial amount, 0.50, times 100%, okay? And let me get my calculator. 0.018 divided by 0.50 times 100%. So that's 3.6%. So since this is less than 5%, it means that the approximation is okay. Whenever you do one of these problems, the first thing you want to do is try the approximation method. Most of the time, it's going to work. Now, let me show you what would happen if the initial molarity had been, instead of 0.50 molar, if it had been 0.050 molar, okay? If that happens, then here is what we get. Ka would equal y squared over 0.050 minus y. Okay, so remember, it's the same as before, except that this time, instead of starting at 0.50, we're starting at 0.050. So we are saying that that would be approximately the same as saying y squared over 0.050. All right, and we're saying that equals 6.8 times 10 to the negative 4. All right, so let's see if we were to use this approximation, what this would come up to. So that means that y is going to be, right, 6.8 to the minus 4 times 0.05. And we're going to take the square root of that. And it comes up to be 5.83 times 10 to the negative 3. So let's say 5.8 times 10 to the negative 3. Let's test the approximation. So that means that 5.8 times 10 to the negative 3 divided by the initial molarity, 0.050 times 100%. Okay, so I'm going to divide this 0.05 times 100%. And that comes up to be about 11, let's say 12%. So as you can see in this case, because that value is 12%, it's more than 5%. In other words, the approximation gives you more than 5%. Therefore, we cannot use this approximation. So you say, well, what do we do then? Well, what you're going to have to do is we have to use the quadratic equation to solve the problem. All right, let me narrow this a little bit. So we're going to have to use the quadratic equation to solve this kind of a problem. All right. Now, let me go back here and give you some ideas here. Okay, I'm going to put this, actually, I'm going to put this over here. This is your next slide here. Actually, yeah, let's just show it here. Oops. Okay, so here's the way we're going to do it then. First of all, you need to identify the species that can affect the pH, which is basically your weak acid. In most cases, because water's autoionization is so small, we pretty much ignore it. We also ignore any hydroxide ion concentration because it's usually determined by the hydrogen concentration. We set up an ice table so we can express the equilibrium concentrations in terms of a single unknown, which I'm using Y again. Hey, you can use whatever letter you want, okay? I don't like to use X because I don't want to get it confused with the X in the times scientific notation. Now we write the Ka in terms of the equilibrium concentrations. We solve for the unknown by the approximation method. We test the approximation, right? We have to test it. And if it is not valid, then we're going to have to solve for it exactly using the quadratic equation. And then we can, if we need to, we can either calculate the concentrations of all the species like we did before in the equilibrium exercises, or we can calculate the pH directly. All right. So that's kind of the way it works. Okay, so I have a problem for you now. This is the next problem. Let's put it up here. So this is, what is the pH of a 0.122 molar monoprotic acid whose Ka is 5.7 times 10 to the negative 4. And once more, I keep losing. I can't find my notes. I keep losing my things. Sorry, guys. I'm scrambling here to find my notes and I keep losing them. Hold on a second. I got that. This guy. I seem to be missing. Oh, here it is. Sorry, I was missing my notes. Okay, here we go. So here we go. So we're going to solve this problem. So I've already set it up here. You can have the ionization. And again, I'm using HA here to symbolize the acid. We're going to do the initial change in equilibrium, in other words, the ice table. So let's start out by writing out what we have. We have the molarity that is given to us. It says is 0.122 molar. And of course, we're starting at zeros here of our acid and our H plus and our conjugate base. We're going to have a change. I'm going to use the letter Y again to represent that change, so that we end up with 0.122 minus Y molar hydrogen ions and Y molar of the conjugate base. Let's start out. So we're going to write out Ka, right? Remember that Ka would be hydrogen ions times A minus divided by HA. So that means that this is going to be Y squared over 0.122 minus Y. And let's start out by testing the approximation method. So we're going to say this is approximately Y squared over 0.122. And we've been told that this is 5.7 times 10 to the negative 4. So that means that Y is going to be square root of 0.122 times 5.7 times 10 to the minus 4. And you want to do the calculations, you can do that. I'm going to tell you what it is right now. It's actually 8.33 times 10 to the minus 3. And again, it's up to you. You can just keep it up 8.3 if you want. Okay, everybody with me? So let's test the approximation. we're going to see if the result we got for this unknown here is less than 5% of the initial molarity of the acid. And I mean, we can do that if you want. 8.33. Where am I? It's point to the minus 3 divided by 0.22 times 100. That's about, roughly about 7%. Which means that we cannot use that approximation method. All right. So what that says is that we're going to have to go to the regular good old quadratic equation. All right. So if you go to your next slide, it has something that looks like this. Okay. Let's go ahead and write out what our values were. Okay. So this is where we started. I have here the, again, the ice table. So we decided that Ka is going to be y squared over 0.122 minus y. We cannot assume that that change is negligible anymore. And this is going to be equal to 5.7 times 10 to the negative 4. And now we have to rearrange that into a quadratic equation that has this form here. Okay, now I'm going to skip all the math. You had to move this over there, multiply out, all this kind of stuff. I'm going to trust that you guys know how to do that. Essentially, the equation you're going to get is going to look like this. Y squared plus 0.00057y. I'm not using scientific notation here just to save space. And minus, well, I guess I did here, 6.5. Tell you what, guys, let me see if I can erase that. Actually, I lost my eraser. Let me do that again. So y squared plus 5.7 times 10 to the minus, let's see, 1, 2, 3, 4. Minus 6.95 times 10 to the minus 5 equals 0. That's the equation you're going to get when you rearrange all that expression that we had up here. Again, I'm skipping the whole math here. I'm hoping you guys can do that. All right. So now the key is we had to find solutions. So you're going to substitute these. So remember, this is A equals 1. B equals 5.7 times 10 to the minus 4. C equals negative 6.95 times 10 to the minus 5. Okay, so you're going to take these values and you're going to plug them in here, right? Okay, so we started out by writing this out. We solved for the equation. We now plug in the possible values in there, and we had to come up typically with 2 possible solutions. And here are the 2 solutions you're going to get. And again, I'll let you do this at home if you want. You have y equals 0.0081 or y equals negative 0.0086. As you can tell, There's no such thing as a negative molarity. So we're going to eliminate that. And that means that this is the value that we will choose. Okay. So now what we're going to do is we can now calculate what is the final pH. All right. So the concentration of hydrogen ions equals 0.0081 molar, which means that the pH equals minus the log of 0.0081 molar. And you can do your calculations there. I'm going to skip it. This is going to come up to be 2.09. Excuse me. So notice that it's a long process. Many times, what's going to happen is your approximation method is going to be sufficient to help you kind of like work it out. So always start with the approximation method. Okay, let me zoom in a little bit here, zoom out a little bit. You guys can see the whole thing. Here we go. Again, remember, pin this screen onto yours so that you can see the full, the big image there. Sorry about the scribble there, I messed up. All right, so essentially that is the way you're gonna work this out, okay? You're gonna be able to look at the acid. They're gonna give you, in this case, they give you a molarity, and they're gonna ask you for the pH of the solution. Start out by writing out, always, what is the ionization equilibrium. Set up your ice table. Start with the approximation method. Excuse me, choking. Once you've done the approximation method, like we did before, test it. And if it's more than 5%, you're gonna have to use the quadratic equation. As I mentioned, I skipped a few steps in here, but you should be able to do the algebra part here. It's usually the stuff that gets everybody a little kind of stumped because it's just hard. And I know some of us are kind of like not very, we've forgotten some of this stuff, but that's the idea with your homework, is to get plenty of practice doing this. All right. Let me do this. Let me see. I don't know what I have here next. Give me a moment here. I'm going to step out for a moment and check something. Hold on a second. Okay, let me I think we're gonna be closing down our session just in a few minutes. Let me give you one more exercise to work on. I don't think this made it into your slideshow. I apologize for that, please. Please forgive me. But here it is. Hold on a second. Gotta get myself organized here. I'm sorry, guys. I'm very disorganized right now. All these papers are kind of like I'm losing track of everything. Oh, here we go. Here it is. Okay. Let me come back here. Okay. Okay, so again, this is being recorded, so hopefully, you can come back and do the exercise again. I realize it's a long time and I don't want to overburden you, but you can read some stuff. There's a couple more things I wanted to go through, but we'll go through them next time, okay? So the plan is we'll meet again on Thursday, same time. We'll have a similar type of setup here. Unfortunately, I don't have a way of toggling on my computer with like touch screen type of stuff. If I had an iPad, I would connect it to here, and then I would be able to kind of like write on it, and it would work out. Oh, somebody says philosophy appetizer. Yes, I'll have a philosophy appetizer for you on Thursday, okay? All right, I'll have one. Actually, I wanted to do it tonight, but I said, you know what, let me test this out first, just to make sure we get this content in. Okay, here we go. Let me come back to our I'm sorry, my little notepad here. Okay, so, oh, great. Hey guys, let me see if I can get this here. I'm having some glare coming in from the window here as the sun sets. Just my sign to, kind of start moving out of here. Oops, sorry. Okay, let me give you a chance to write this down. Again, I don't think this slide made it into our slideshow. I'm gonna step off screen for a moment. I need to close the shades here in my house so it doesn't work, so it doesn't interfere, okay? Just give me a few seconds while you write that down. Let's see, while we do this, Denise, you were asking about exams. We're not there yet. We haven't decided here with the faculty. We're working on that, some of the possibilities. So please bear with us. Just know there's not going to be an exam before spring break, okay? Don't worry about it. There will be this coming quiz, and hopefully it'll be a second quiz that we'll have by next week. I'll post it up. And probably that's as far as we're going to be able to get besides the homework and then a couple of labs that will get done between now and then. Since, we are going to give you the data for the labs, you won't get to basically have the hands-on experience. But I feel like the idea of that first experiment we did where you guys tried out different kinds of reactions, pretty much most of what you will be doing for these labs is essentially the same. The only difference is, some of them you filter, some of them you don't. Some of them you confirm the reaction by doing some extra reactions and stuff like that. But it's all explained in your lab manual, and we'll give you the visuals for it, okay? So that's all that's going to happen. Please don't worry about your, what do you call it? Your exams. Can we work with a partner for lab assignments? Yeah, of course you can, except social distancing, right? So yeah, if you want to work with somebody, that's fine. Now, everybody's gonna get their own unknown. So you don't need to work with a partner for it, but if you want to, that's fine. In other words, I don't know, it's gonna be rather random. So, if you know that one of your buddies has the same unknown as you want to work together, that's fine. You know what I said on day one in class, I trust you guys. I'm not into kind of like, oh, I don't want people to cheat and that kind of stuff. No, I trust you guys. I want you to learn. We are undergoing some pretty unusual situations here, and we're doing the best we can. And again, I want to tell you this again, and I'll say it over and over. I'm very proud of you, and I appreciate your effort that you're putting. Okay, so here's what I have on the screen. Let me take this from the bottom here because it's kind of like getting in the way visually. Can we put it back on here? Okay, so here's the thing. Earlier, you saw a table where they showed you the Ka values of different acids. Now, if you are training your mind scientifically, you would ask the question, how do you find that? How do you find the Ka of an acid? So this is the last exercise we'll do today. I'm going to work you through this one. So it says here that the pH of a 0.10 molar solution of formic acid is 2.39. What is the Ka of the acid? Right? So this would be the experiment where you actually find out what the Ka is. Now, what we're going to do later in the semester is, and I don't know if I'll get this in before spring break or not, but it's going to be essentially a dry lab. I'm going to give you some data later on, and what you're going to do is you are going to use 4 different methods for finding the Ka of an unknown weak acid. Believe it or not, that's how many methods there are. So let's try this one here. This is one where you make a solution of the acid and you find the pH of the solution. All right. So let's go ahead and start out by writing out our ice. So let's start out by writing out the equation. So the formula is HCOOH. Remember that this is, as soon as you see that formula, a little alarm should go in your head. Oh, that's what they call a carboxylic acid. Remember, it has a hydrogen that's connected to the carbon that's not acidic. The hydrogen that's going to be ionized will be the one that's attached to an oxygen. It's an oxy acid. And again, I'm going to use the shortcut formula here. I'm going to simply say H plus and HCOO minus. So those are the products of the ionization. So let's start out our ice table, and we'll go with molarity here. It says this is 0.10 molar. And of course, we start out with no ionization products. Let's see what the change is. Again, I'm going to use, Y. And then at the end of the process, we'll have 0.10 minus Y, Y, and Y. Okay? Now, the difference in this case is we know what the value of Y is. How do we know that? Oh, because we have the pH. I'm looking for my highlighter. We have the pH. So from the pH, we can calculate, right, that the concentration of hydrogen ions would be 10 to the minus the pH, right? That's what we learned earlier. So let's see what that is. And again, you'll have to figure out your calculator how it works. So I'm going to put in 2.39 negative of that, and then I'm going to 10 to the that, whatever that is, and I get 4.07. You know what? Since the pH here has 2 decimals on it, that means that's 2 significant figures. So that means that the concentration of hydrogen ions would be 4.1 times 10 to the negative 3. And guess what? That is exactly what the value of Y is, right? In other words, Y is essentially the molarity of hydrogen ions, and we get that from the pH. So now we want to find out what is the value of Ka. Well, at equilibrium, of course, Ka is hydrogen times the ion, which is called the formate ion, divided by the concentration of unionized acid. But we know that is essentially Y squared over 0.10 minus Y. And in this case, we have the option. We can choose to approximate or not. I think as we go along, we'll learn some tricks about how to look at a problem and kind of decide whether, it's going to work to approximate or not. But in this case, it doesn't matter because we actually know what y is. In other words, Ka is going to be 4.1 times 10 to the negative 3 squared divided by 0.10 minus 0, oops, sorry, messed up. 4.1 times 10 to the negative 3. Sorry, I'm using this very dark marker so that you guys can see it. And I realize that I don't have an eraser with me, so, but I'd rather do that. All right, so sorry about that mess in there. Again, if I had an iPad with a touchscreen, I would be able to erase those kind of things. I have a colleague, Professor Nancy Roback. She's a whiz with these kind of things. She's the one that's been kind of helping me set up all these things. Okay, so again, I'm not exactly sure how your calculators work. Mine is a very rustic calculator, all right? So I have to do all kinds of crazy stuff here to do this. But what I'm gonna have to do is first, I'm gonna have to subtract this 0.1 minus 4.1 to the minus 3, that's that. And I'm gonna have to put that in my memory. And then I'm gonna take the top here, 4.1 to the negative 3. And I'm gonna have to square that. And I'm gonna divide that by what I had in the memory. And fingers crossed, this is gonna work out. So I get 1.75 times 10 to the negative 4. And again, because this is only good to 2 sig figs, we're going to have to put it 1.8 times 10 to the negative 4. Right? And let me give you a few more seconds for you guys to work through that. If you're getting the same numbers, is anybody getting a different number? Just let me know, okay? Because I may have messed up. But how do you check? Thought you'd never ask. I'm going to come back here to that table that I showed you earlier. Remember the table with the different constants? Let me zoom in here. Oops. See formic acid there right underneath HF. Wait for it. Wait for it. Oh, look at that. It is actually 1.8 times 10 to the negative 4. So that is one way in which you can find the Ka value of a weak acid. All right, you basically set up a solution of known molarity and you check the pH. In a dry lab that you guys are going to do later on, which I'll post on Canvas, there are other methods that you can use. However, I'm going to wait a little because a couple of those methods, actually 3 of those methods, depend on stuff we're going to be studying over the next few weeks. All right. Let's see. Okay, so let me ask some. Let me see some of the questions you guys have here. All right. The hydrogen attached to oxygen is the only one that is ionized. Yes, that is correct in this case. Okay, this acid is what we call a monoprotic acid. Remember, it only has one ionizable hydrogen. And if we go back here to that chart that I was showing a little while ago, let me zoom in again. Okay, you can see the formula here next to the formic acid, right? You can see it here. And you can see, maybe you can't see here the color, but in the original one here, that hydrogen that's in there connected to the oxygen, that's the one that ionizes. So it's very similar to other carboxylic acids. You can see down here, acetic acid. And you can see similarly, there's a hydrogen that is connected to an oxygen. That is what we call the acidic or ionizable hydrogen. Notice that there's other 3 hydrogens connected to carbon. Those remain attached. They don't ionize out. These are what I call carboxylic acids. They are all of the oxy acid variety. The other thing is, and I guess if we had the time and I didn't want to overburden you, we would be talking about polyatomic, what am I saying? Sorry, polyprotic acids. These are the ones that have more than 1 hydrogen on the formula that actually ionizes. So let's see. Yes, Azadeh, go ahead and open your mic and let me know what you need.
Do we have lab today, Professor, or we are off at 7?
Great question. No, I wasn't planning on having a lab session. I'm going to use that time personally to set up your lab that you're going to be doing so that it'll be ready by tomorrow. But thanks for asking.
Thank you so much.
No problem. Hey, by the way, Azadeh, thanks for giving me that heads up on how to do the notes app from your husband.
Sure, anytime. Any other question?
And send him my regards. Hope he's doing better, okay?
Thank you so much.
You're welcome. Okay, so what we're going to do is, I don't know if I want to do this or not. It's kind of like a little, you know what, guys, let me go ahead and do this just so I can say that I did it. But if you want to check out right now, that's fine. This next part is an explanation of why is it that when we do these problems, when the molarity of the acid is lower, you can no longer use the approximation method. Basically, it's called the percent ionization, all right? Percent ionization, all right? And again, I'm going to use the slide here. Look at the formula for percent ionization. It says, what is the ionized acid concentration at equilibrium divided by the initial concentration of acid, right? Now, remember that if I have a weak acid and it's what we call monoprotic, right? Let's say we had HA ionizing into H plus and A minus, right? That was our formula. So technically, the percent ionization would be the molarity of the ionized form of the acid divided by the initial concentration of the acid times 100%, right? That's the initial concentration. Notice that it's the same formula that we used to test whether we could use the approximation or not, right? Because in this case, at equilibrium, the concentration of the ionized form of the acid equals the concentration of hydrogen ions. So, you know, technically you could use either one once you've solved your ICE table to do this. So notice that essentially this percent ionization is what we used. This is the same that we used. Sorry, my paper is kind of sliding here. To test the approximation method. If you notice before, in the 2 problems we did, where we did one where we calculated the pH of an acid solution, where it was like 0.5 molar, and we were able to use the approximation method. You remember that when we did the same exercise with a smaller concentration of the acid, we could no longer use it. Look at this chart here. Let me zoom in a little so you can see it a little better. Again, remember, with a strong acid, it doesn't matter what the initial concentration is, because it's going to essentially have full ionization. In other words, the concentration of the ionized form is the same as whatever the initial concentration was of the acid. But look at the chart for a weak acid. Notice that as the concentration decreases, right? So as the initial concentration of the acid decreases, let me zoom back in a little bit. The percent of ionization increases. So that's why, you know, at a certain, and again, this is all going to depend on the particular acid, but you can see how at a certain kind of threshold somewhere in here, and anything lower than that, it seems like you can no longer use the approximation method once you get there. Because notice that for large, higher concentration of the acid, there is really no change in the ionization. But as you get to smaller and smaller concentrations, the actual ionization starts increasing. What that means, of course, is that the value of the hydrogen and the ionized acid concentration is going to be higher, which means you can no longer neglect or discard that Y value, that variable that we calculated in the ice table, right? And the question is, how does this happen? There are several explanations for why this happens. I'm just going to give you a very simple kind of like tourist version kind of explanation just to close out here. So let's say that I am at a high initial concentration of my acid. All right. So in this case, my Ka is going to be, x squared, or let's say y squared over my initial concentration of acid minus y. Now, in that case, since this value here is so large or relatively large, essentially it's okay to assume that the value of y is negligible with respect to the initial concentration of the acid. Now, let's go now to a low value of my initial concentration of acid, okay? Let's call it HA prime. Again, let's write out the equation. This would be y squared over, this is now HA0 prime minus y. Now remember what happens now, right? This value here is smaller, right? This is a smaller value than it was up here. In order for this to remain constant, again, remember what we talked about ratios. If I need to keep a ratio constant, right? If I decrease this thing here, right? That means that the value of y has to increase, right? In other words, otherwise, this is not going to be able to catch up, right? So basically, what's going to happen is that this is going to be larger. So that's one way of looking at mathematically. I'm just telling you, one of the different explanations. The other explanation has to do with the Le Chatelier principle, right? Remember when we studied equilibria and we said that, for example, with gases, we said that when we change the numbers of moles of gases, the side of the equation that has the larger number of moles of gas is the one that gets affected most, right? And therefore it determines which way the equilibrium goes. So again, if we look at the equilibrium here, remember that if I lower the concentrations, the right side of the equation has 2 particles for every particle in here. That means that the right side of the equation, quote unquote, feels the decrease in the concentration more than the left side. And therefore, since the right side, quote unquote, feels the decrease more, that means that if you look, remember that the kind of like seesaw idea, the teeter-totter, right? What that means is that now the right side is the one that's feeling like it's kind of like lighter. So the left side is feeling it less, the right side is feeling it more, that decrease, which means it forces by Le Chatelier for the equilibrium to shift more to the right. In other words, to generate more of these ionized particles, okay? Like I said, these are kind of like a little bit of sketchy explanations. I don't need you to really know all the reasons. All I need you to remember is this point, that as the concentration of the weak acid decreases, you have a possibility that the approximation method is not going to work because the acid is going to ionize more. That means that that value of y you calculate is no longer negligible, okay? And that's all I need to know. Now, you might want to ask, excuse me, get some water. Your question will probably be, how do I know? When do I decide? The answer is most of the time you don't. You basically start out, like we said, with the approximation method. And then what you do is you test. As time goes on, you'll start getting some hints, both from either the value of the Ka or from the actual molarity of the acids, as to whether you're going to have to do the quadratic equation or not. But I would say, for the most part, always start with the approximation method, okay? What I'm going to do is I'm going to scan these things that I that I just wrote here, and hopefully you guys can make sense of these. All right. So I'm going to pull this out of here for a moment. Okay. So let me come back here to my face again so I can see you guys. All right. There I am again. As I was saying, I am going to take those pages that I wrote on, and I'm going to scan them and post them in the probably in the lectures module, and that's also probably where I'll post the recording of this session. Hey guys, you know what? This was a lot longer than I anticipated. Originally, I was going to think we're going to go for kind of hour, but I guess I got carried away. Sorry. So let me know if there are any other questions here. You can either, just unmute your microphone and ask, or do the raise hand thingy, or just post it on the group chat, and I can tackle those. I'm going to give you a couple of minutes for that, and then what I'm going to do is I'm going to stop the recording at that point so that my system can start processing it. It's going to be a fairly large thing. Just so you know, the way I do it is I record this to my hard drive, and then what I do is upload it to a YouTube channel, and then I'll give you guys the link that you can watch it on YouTube, okay? The reason is I cannot directly upload video files into Canvas because they're too large. I work with, believe it or not, there was a time in my life when I actually produced videos for a nonprofit organization. And I worked side by side with an actual movie director. And he told me, if I remember correctly, that it takes 1 gigabyte for every 15 minutes of video that you download or produce or whatever it is. Anyway, just thought I'd throw that out there. That was my way of saying, hey, there was a time when I kind of like hobnobbed with some movie director. Hey, I've done quite a few things in my life. Like I told you that time that I told you about the generation flux and how the ability of kind of like switching between one career and another one. That's me, man. Okay, let me give you a few more minutes. If you have any questions you want to ask, either post them on the group chat. And thank you, Emily. Or not, maybe unmute your phone and ask your question. If you don't have anything like that, let's see.
Professor, you're doing great.
Thank you. Okay. Jenny, you're offering to help people with their algebra. Sure, if you want to make a short video, let me know and we'll put it up there too. Thank you. Thank you, Thomas. I appreciate it. Hey guys, let me say it again. Okay, I know it's getting to be kind of like maybe it keeps going on and on and on, but I just want to tell you guys I'm very proud of you. You guys are doing great. Thanks for joining in. And if you were not able to join us and you're watching the video, let me know if it works. And if you have any questions, you can, again, remember, you can email me. You can put a message in the inbox of Canvas, or you can text me. You have my text number in the syllabus, and you can reach me there also. Again, give me a little time to respond because sometimes I'm kind of wrapped up with my other class, my Chem 1A class, and of course my own personal things, but it's not a whole lot of that. I'm trying to turn my head so that it won't be, that my screen won't glare my glasses, but I don't have the anti-glare glasses. Thank you guys for being here. And yes, repeat what Azadeh just said. Stay safe, everyone. Hey, we're going to write this out. It's all going to work out. We're going to get you through. You are going to be able to finish your semester. You'll get your grade. You'll get to, do your transfer, whatever you need. Okay, we'll make it happen. Don't worry. And if you are worrying or you're concerned about your status, please let me know. If I don't have the answers, I'll try to get the answers for you. I'm talking about like administrative stuff, which I really honestly don't know a whole lot about. Okay, I'm going to stop the recording here so we can start processing it, but I'm going to stick around for a few more minutes in case anybody has any other questions. Okay, so I'm going to start.